You look in the mirror every single day. You see your face, you fix your hair, you walk away. And in those few seconds, something absolutely insane just happened. Something no school ever taught you. Something that took the greatest minds on Earth most of the 20th century to even begin to understand. The light hitting your reflection did not simply bounce. It was absorbed, re-emitted, interfered with itself across every single point on that surface, got tangled up in a quantum debate that started in 1908 and technically is still going, and was shaped by a force that emerges from literally nothing, from empty space itself. And the mirror you looked into this morning? It is coated in a layer of silver so thin that if you stacked 1,000 of those layers on top of each other, the whole pile would still be narrower than a single human hair. Yet that invisible sliver of metal is executing a process so mathematically intricate that the most precise theory in all of science is required to describe it correctly. And even then, physicists argue about the details. This is not metaphor. This is not science fiction. This is what happens every single time you look at your own face. The bathroom mirror is the most deceptively ordinary object in your home. You think you understand it. You learned in school that light bounces off it the same way a ball bounces off a floor. Angle in equals angle out. Clean, simple, done. But that picture is completely wrong. Not approximately wrong. Not wrong at the edges wrong. Fundamentally, structurally wrong at every level below the scale your eyes can see. And the true story, the actually correct story, involves quantum probability, collective electron behavior, vacuum fluctuations from empty space, a 100-year argument between two physicists, and a mirror made from 200 atoms that was built in a German laboratory in 2019. We are going to walk through all of it. If you value documented physics explained at this level of depth and with real sources, subscribe right now. It is the best way to support our work. Comment below and tell us what city you are watching from. We read every single one. This script is researched and factual. We draw from two primary sources that the casual viewer never encounters. First, Richard Feynman's 1985 book, QED, The Strange Theory of Light and Matter, published by Princeton University Press. This book was transcribed from his public lectures at UCLA, and Feynman himself said, and this is documented, to learn QED, you have two choices. You can go through 7 years of physics education or read this book. We read the book. Second, a peer-reviewed paper titled Photon Reflection by a Quantum Mirror, a Wave Function Approach, authored by R. A. C. Correa and Pablo L. Saldanha, published in Physical Review A, Volume 93, February 2016. This paper derives from a mathematical first principles, the exact momentum exchange between a photon and a mirror during reflection, not assumed, derived, and in doing so contributed to one of the oldest unresolved debates in modern physics. Both sources are real, technical, and verifiable. Now, let us tell the story. Let us start at the surface. A standard bathroom mirror has a thin layer of metal, aluminum in most consumer mirrors, silver in precision optics, deposited on the back of a glass sheet. Modern protected silver mirrors, the kind used in scientific instruments, telescopes, and laser systems, have a silver coating between 80 and 120 nanometers thick. A nanometer is 1/1000th of a meter. That silver layer is then capped with a film of silicon dioxide, ordinary glass, essentially, as a protective overcoat, because without it, silver oxidizes and tarnishes, and its reflectivity collapses from above 95% down to something visibly dull within months. The whole construction, silver plus protective cap, might be 150 nanometers from the glass surface to the outer layer, about 400 times thinner than a red blood cell. A clean protected silver mirror reflects between 95 and 99% of visible light across the 500 to 800 nanometer range of wavelengths, according to optical manufacturers including Edmund Optics in Barrington, New Jersey. That means only 1 to 5% of incoming photons are absorbed. The absorbed photons convert entirely into heat, a process called phonon generation, where the absorbed photon's energy goes into vibrating the metal's crystal lattice. But here is the first quantum twist, and it is a genuinely strange one. Which individual photons get absorbed and which ones get reflected is not determined by any property of the photon that you could measure before it hits the surface. It is determined only at the moment of interaction, and it is pure quantum probability. Physicist Rüdiger Pachotta, CEO of RP Photonics Consulting in Switzerland and a leading authority on optical components, stated clearly in Scientific American in February 2024, each photon that strikes a metallic mirror faces a binary outcome, complete reflection or complete absorption, not partial reflection, not the photon losing a little energy and continuing. If you fire single photons at a 97% reflective mirror, 97 times out of 100 you detect the photon bouncing back. The other 3 times, the photon is entirely gone. Its energy converted to heat, one quantum of vibration deposited into the metal lattice. The photon that was absorbed did not give a fraction of itself to the mirror and escape weaker. It ceased to exist as a photon. This is a fundamental feature of quantum mechanics. A photon cannot be partially absorbed, only wholly absorbed, or not at all. The probability for any given photon is fixed by the mirror's reflectivity. The outcome for any specific photon is random. This is already far stranger than Newton's billiard ball light, but we have barely started. What is actually happening inside the silver? Silver has atomic number 47, 47 protons in its nucleus, 47 electrons orbiting around it. Its outer electron configuration is arranged so that the outermost single electron, sitting in what chemists call the 5s orbital, is barely attached. Silver crystallizes in a face-centered cubic lattice, and in this arrangement, that outermost electron is freed from its parent atom entirely, joining a collective sea of mobile conduction electrons shared across the whole metal. These free electrons are the key to everything. Silver has the highest electrical conductivity of any element, higher even than copper, which is why copper needs to be thicker than silver wire to carry the same current. That extraordinary conductivity reflects the extraordinary density and mobility of silver's free electrons. Roughly 1 free electron per atom, and with 6.2 times 10 to the 28th electrons per cubic meter of silver, that is a sea of charge dense enough to respond almost instantly to any incoming electromagnetic disturbance. When a photon arrives at the silver surface, when the oscillating electromagnetic wave of the photon meets the silver, those free electrons feel the oscillating electric field and begin to oscillate themselves at the same frequency as the incoming light. Oscillating electric charges radiate electromagnetic energy. The oscillating electrons, driven by the photon's field, re-emit a new electromagnetic wave at the same frequency. This re-emitted wave travels backward, away from the silver surface and back the way the photon came. That is reflection. The silver did not bounce the photon like a wall bounces a ball. The silver absorbed the photon's electromagnetic field, used it to drive free electron oscillations. And those oscillations generated a new photon going in the reverse direction. The silver is a quantum antenna that receives and retransmits. This is why metals are shiny and insulators are not. Glass, silicon dioxide, has no free electrons. Its electrons are all tightly bound to specific atoms and cannot oscillate freely in response to visible light. Glass transmits light rather than reflecting it. Metal has free electrons that respond to incoming visible frequency electromagnetic waves, reflect them, and appear shiny. Simple rule. Deep physics. Silver outperforms aluminum across most of the visible range because its free electron response is flatter and stronger at those specific frequencies. Gold absorbs blue and green wavelengths, reflecting red and yellow, giving gold its characteristic color. Aluminum, while cheaper, drops in reflectivity in the ultraviolet and is less efficient than silver in the 400 to 800 nanometer visible band, according to data from Edmund Optics. For household mirrors, aluminum is used because it is cheaper and easier to deposit at scale. For astronomy, for laser cavities, for scientific instruments, protected silver is the standard because its reflectivity exceeds 95% continuously from the near ultraviolet through the near infrared. A 2024 study published in Helion investigated which dielectric adhesive materials best protect the silver film against peeling and oxidation in long-duration telescope use. The substrate tested was a glass disc 25 millimeters in diameter. Materials tested included aluminum oxide, silicon dioxide, titanium dioxide, magnesium fluoride, and niobium oxide. The silver itself had to be deposited at temperatures below 150 degrees Celsius to prevent oxidation during the coating process. Even the manufacture of a mirror, not the quantum physics of it, just the industrial creation, requires precision at the nanometer scale and detailed knowledge of how electrons in different crystalline structures bond to silver. The silver works. The manufacturing is centuries old. Justus von Liebig, a German chemist, developed the silver mirror reaction in the mid-1800s. Silver nitrate and a reducing sugar sprayed onto glass, and versions of that chemical process are still used today in household mirror production. Liebig's chemistry produces the reflecting surface. Quantum electrodynamics explains why it reflects. But none of this, not the free electrons, not the oscillation, not the retransmission, explains why the angle of incidence equals the angle of reflection. That rule is not obvious from the physics described so far. Electrons can oscillate and re-emit in any direction. Why does the re-emitted light go specifically in the mirror symmetric direction from the incoming light? Why not sideways? Why not straight back? This is where classical physics runs out of answers, and quantum electrodynamics, QED, takes over completely. Richard Feynman, Nobel Prize, 1965. QED, the theory of how photons interact with electrons. Feynman built this theory alongside Julian Schwinger at Harvard and Shinichiro Tominaga in Japan, independently in the late 1940s, and Freeman Dyson proved their approaches were equivalent in 1949. QED is the most precisely tested theory in the history of science. Its prediction of the electron's anomalous magnetic moment, a quantity called G minus 2, agrees with experiment to 1 part in 10 billion. That is like predicting the distance from New York to Los Angeles to within about half a millimeter. QED works. In QED, a photon does not travel from point A to point B in a straight line. It simultaneously explores every single possible path from source to detector, every point on the mirror surface, every angle, every indirect route through the wall or ceiling or floor, all at once. This is the path integral, the sum over histories. Each path contributes a probability amplitude, Feynman's little arrow, a tiny spinning clock that accumulates phase at a constant rate as you trace the path through spacetime. At the detector, you add up all the arrows from all the paths, and the length of the final combined arrow squared gives you the probability of detecting the photon. Divide the mirror into sections. Label them A through M from left edge to right edge. A photon traveling from a light source on your left to a detector on your right has a probability amplitude contribution from every single one of those sections. Section A, at the far left edge, contributes an arrow with a certain phase. Section B contributes a slightly different arrow. Section M at the far right edge contributes yet another. Now add them all up. The arrows from sections near the edges, A, B, C, and K, L, M, are pointing in wildly different directions because the path lengths via those edge sections are very different from each other. They cancel. The arrows from sections near the center, E, F, G, H, I, are pointing in almost the same direction because those paths take almost the same amount of time and their phases are almost identical. They add up. The sum is dominated by the central paths, and the central paths are precisely the ones where the angle of incidence equals the angle of reflection. The law of reflection, angle in equals angle out, is not a law of nature. It is the geometrical consequence of constructive quantum interference at the classical path. QED derives the classical result from quantum probability. The rule emerges from the math of the universe, not from a postulate. Feynman demonstrated this with a physical experiment. Take a mirror and remove the edge sections, sections A, B, C, and K, L, M, leaving only the central section. The reflection is unchanged because the edges were canceling out anyway and contributed nothing to the observed reflection. Now take a different mirror and scratch alternating sections into a diffraction grating. Remove the sections where arrows point in one direction, keep the sections where they point in another. Now the arrows that used to cancel each other no longer do. The light reflects at new angles that classical optics says are impossible. You made a mirror reflect in directions it should not reflect, purely by removing some of its surface. This is the diffraction grating. It exists, it works. It is used in spectrometers and laser systems worldwide. QED predicts it exactly, real, measurable, quantum. Now, let us talk about depth. The photon does not interact only with the absolute outermost layer of silver atoms. The electromagnetic field penetrates into the metal before the free electrons collectively respond. The depth of penetration before the field decays to about 1/3 of its surface value is called the skin depth. At visible light frequencies, wavelengths of 400 to 700 nanometers, the skin depth in silver is roughly 10 to 20 nanometers. This is why a silver coating needs to be at least 80 to 100 nanometers thick to function as a good mirror. Much thinner than the skin depth, and you are not capturing the full free electron response, and you get partial transmission. An ultra-thin metallic film, a few nanometers thick, has equal reflectivity and transmissivity, and absorption peaks at 50%, as reported in research published in the Journal of the Optical Society of America B in 2018. The mirror only becomes a mirror when it is thick enough that the electromagnetic field can interact with enough mobile electrons to generate an efficient back emission. Laser cavities require even better mirrors. Dielectric mirrors, made of alternating layers of silicon dioxide and titanium dioxide instead of metal, can reflect more than 99.9% of light at a specific wavelength. Each individual layer pair reflects only a tiny fraction. But stack 15 or 30 pairs together, each pair precisely 1/4 wavelength thick at the target frequency, and the reflections from all those interfaces add up coherently through constructive interference until virtually nothing gets through. Dielectric mirrors and gravitational wave detectors like LIGO in Washington State and Louisiana reflect above 99.999% at the laser wavelength of 1064 nanometers. Fewer than 10 photons per million are lost per bounce. Even those rare absorbed photons matter because each deposits a quantum of heat that vibrates the mirror surface, and LIGO needs to detect mirror movements smaller than 1,000th the diameter of a proton. Quantum optics, thermal physics, and precision engineering collide at the mirror surface. Your bathroom mirror is none of that. Your bathroom mirror does not need to be. It just needs to be good enough to show you your face, and silver plus glass does that with 96 or 97% fidelity, which is more than sufficient. But even your bathroom mirror is experiencing a force from nothing. This is real. This is measured. This is confirmed. And it happens to every surface in the universe. The Casimir effect. 1948. Hendrik Casimir, Dutch theoretical physicist, working at Philips Research Laboratories in Eindhoven on a completely unrelated problem about colloidal chemistry. He was trying to figure out why large molecules in a colloidal solution did not attract each other with the strength predicted by London van der Waals equations at longer separations. The discrepancy was real and unexplained. Niels Bohr, in a brief corridor conversation, suggested the explanation might lie in zero-point energy, the irreducible minimum energy of the electromagnetic vacuum. Casimir went back to his office and calculated what would happen if you placed two perfectly conducting metal plates parallel to each other in a perfect vacuum with no charges and no external fields. Quantum mechanics says the electromagnetic field at every point in space cannot be perfectly zero. It has a zero-point energy, a ground state fluctuation that cannot be eliminated. The field fluctuates continuously, generating virtual photons, quantum fluctuations of the electromagnetic field that come and go too quickly to be directly detected, but that nonetheless exert pressure on nearby conducting surfaces. When you insert two parallel conducting plates into this fluctuating vacuum, the geometry changes what modes of the electromagnetic field can exist between the plates. Only modes whose wavelengths fit a whole number of times into the gap can be supported between the plates. All wavelengths exist outside the plates without that restriction. The result? The density of electromagnetic modes between the plates is slightly less than outside the plates. The vacuum radiation pressure, pushing inward from outside, is slightly greater than the vacuum radiation pressure pushing outward from between the plates. Net result? An attractive force pulling the plates together. Casimir derived the formula for this force. For two perfectly conducting parallel plates of area A separated by distance d, the force equals pi times Planck's constant times the speed of light divided by 480, multiplied by A, divided by d to the fourth power. Notice what is not in that formula. No charge, no mass, no material property. Only Planck's constant, the speed of light, and the geometry. The force scales as the inverse fourth power of the separation distance. Double the distance, the force decreases by a factor of 16. Halve the distance, the force increases by a factor of 16. At very small separations, this becomes one of the dominant forces between surfaces. For plates 1 micron apart with 1 square centimeter of area, the Casimir force is roughly 1/10 of a micronewton. That is the weight of a few grains of pollen. Tiny by human scales, enormous by nanoscale engineering standards, where this force can cause nanoscale devices to stick together irreversibly, a phenomenon called stiction that is one of the primary failure modes in microelectromechanical systems, or MEMS. Marcus Sparney at Philips in Eindhoven first attempted to measure the Casimir force in 1958 using flat metallic plates of aluminum, chromium, and steel. He measured with a spring balance calibrated by capacitance between the plates. His conclusion: results did not contradict Casimir's prediction. Not proof, but not disproof. The force was too small and the alignment too imperfect for decisive confirmation. 1997, Steve K. Lamoureux at the University of Washington in Seattle. He used a 4-centimeter spherical lens and an optical quartz plate, both coated with copper and gold, connected to a torsion pendulum, a horizontal bar suspended from a tungsten wire, enclosed in a cylindrical vacuum vessel. When he brought the lens and plate together to within a few microns of each other, the Casimir force pulled them and twisted the pendulum by a measurable angle. His results agreed with Casimir's prediction to within 5%. This was published in Physical Review Letters, volume 78, in 1997. First unambiguous quantitative confirmation of the Casimir effect. In 2001, Giacomo Bressi, Gianni Carugno, Roberto Onofrio, and Giuseppe Ruoso at the University of Padua in Italy finally measured the Casimir force between two parallel flat plates using microresonators, achieving the geometry Casimir originally proposed. The confirmation was complete. The vacuum pushes on your mirror, right now. It has always done so. It will always do so. The force is too small to matter for the structural integrity of your bathroom mirror, but at the nanoscale, in transistors and MEMS devices, in the precision optics of gravitational wave detectors, the Casimir force is a real engineering constraint that has to be accounted for in design calculations. Now, let us address the oldest ongoing argument in quantum physics, the Abraham-Minkowski debate. This argument is about the simplest possible question: how much momentum does a photon carry when it is inside a material medium? In vacuum, the momentum of a photon is Planck's constant times the wave vector. Clear, agreed, uncontested. But inside glass, or water, or silver, where the refractive index n is not equal to 1, here, two brilliant physicists disagreed by a factor of n squared, and nobody could resolve it for a century. Hermann Minkowski. In 1908, the photon momentum inside a medium is the vacuum momentum multiplied by n. The momentum increases when you enter a denser medium. Max Abraham in 1909. The photon momentum is the vacuum value divided by n. The momentum decreases when you enter a denser medium. One says multiply, one says divide. They cannot both be right, except, as it turns out, they both are. Experiments were conducted across the following decades and could not decisively resolve it. In 1951, Jones at the University of Aberdeen measured radiation forces on a mirror in a refracting liquid and found evidence for Minkowski. In 1978, Jones and Leslie conducted more careful measurements and again found Minkowski. In 2008, Shi and colleagues in Shanghai pushed a silicon nanofiber with a laser and found evidence consistent with Abraham. Nature Physics published a feature in 2007 noting the ongoing impasse. This debate lasted from the birth of the automobile age to the iPhone era. The resolution came not from a new experiment, but from a deeper conceptual understanding. As Stephen Barnett and Rodney Loudon argued in their 2010 paper in the Philosophical Transactions of the Royal Society, both formulas are correct because they are measuring different physical quantities. Minkowski momentum is the canonical momentum of the photon, the wave mechanical quantity associated with wavelength and phase, the momentum relevant to interference and diffraction phenomena. Abraham momentum is the kinetic momentum, the actual mechanical push delivered to matter, the quantity relevant to Newtonian force calculations on atoms and bulk materials. The photon, being a quantum object with simultaneous wave and particle nature, exhibits both momenta in different experimental contexts. Which one you observe depends entirely on what you're measuring and how. When Correa and Saldana published their February 2016 physical review, a paper deriving the photon mirror momentum exchange from first principles, they showed that a quantum mirror, a mirror with non-negligible positional uncertainty compared to the photon's wavelength, ends up in an entangled quantum state with the reflected photon. The mirror and the photon become correlated. The momentum exchange links them. In everyday life, this entanglement is unmeasurably small because mirrors weigh grams and photons carry momentum of roughly 1 × 10 to the minus 27th kilogram meters per second, an inconceivably tiny number. Your bathroom mirror's quantum entanglement with each reflected photon is buried so far below any detectable signal that it effectively does not exist for engineering purposes. But in principle, it is there. Every reflection creates a quantum link between the photon and the mirror, instantly erased by the mirror's thermal noise. Entanglement from a bathroom mirror, in principle. In 2019, a team at the Max Planck Institute of Quantum Optics in Garching, Germany, made this principle visible. Jun Rui and colleagues trapped exactly 200 rubidium atoms in a two-dimensional optical lattice formed by crossed laser beams. The atomic ensemble had a diameter of about 7 micrometers and a thickness of 10 nanometers. They directed laser light at it. The ensemble reflected about 60% of the incoming light, not through any metallic mechanism, not through free electrons, but through collective quantum behavior. Each individual rubidium atom hit by a single photon would scatter only a tiny amount of light, far less than 60%. But because the atoms were arranged in an ordered lattice with regular spacing, their individually scattered waves interfered constructively in the backward direction and destructively in every other direction. The result was coherent reflection from 200 atoms acting as one. The photons striking the mirror created correlations between the atoms, quantum entanglement mediated by light. The atoms were linked together through the shared photons. As Jun Rui stated in the Max Planck press release, this mechanism of photon-induced correlations between atoms had been largely neglected in quantum optics before this experiment. If those atoms were cooled to absolute zero and all thermal motion removed, the theory predicts 100% reflection from 200 atoms. A perfect mirror the size of a bacterium, sustained entirely by quantum coherence and collective behavior, containing no metal, no glass, no engineered material, just atoms and the quantum rules governing how their scattered waves interfere. And in January 2026, the University of Amsterdam pushed this further. Researchers Hoekstra and van der Groep demonstrated a switchable quantum mirror made from a monolayer of tungsten disulfide, a two-dimensional transition metal dichalcogenide, 1 atom thick, integrated into a photonic cavity. In its default state, the tungsten disulfide monolayer supports excitons, bound pairs of an excited electron and the positively charged hole it leaves behind when it is kicked upward in energy by absorbing a photon. These excitons interact strongly with light at specific wavelengths near 621 nanometers in the red visible spectrum. The cavity enhances this interaction, and the device reflects red light efficiently, a functioning mirror. Apply a gate voltage to inject additional electrons into the material, and the excitons are suppressed. Without excitons to interact with the incoming light, the device absorbs all red light instead of reflecting it. The mirror switches off. Remove the voltage, excitons reform, reflection returns. The switching happens in microseconds with no mechanical movement, no shutter, no actuator. Pure quantum state control over a 1 atom thick layer, electrically modulated. The device was demonstrated at room temperature, which matters enormously for practical applications. Many quantum optical effects only work at temperatures near absolute zero, requiring expensive cryogenic equipment. This one worked at the temperature of your office. The implications for optical switching in quantum communication networks, where photons carry quantum information across fiber optic links and need to be routed and redirected at quantum speeds, are direct and significant. Now pull all of it together. Stand in front of your bathroom mirror tomorrow morning. What is actually happening? A photon is emitted from your bathroom light. In quantum electrodynamics, that photon simultaneously explores every possible path from the light source to your eye, including paths through the mirror. For paths going via the mirror, every single point on the silver surface contributes a probability amplitude. Most contributions cancel by destructive interference. The contributions from a band of mirror points near the classical reflection angle add constructively and dominate the total probability. The photon is overwhelmingly most likely to be detected traveling from source to silver to eye along the classical angle, in E equals angle out path. But it was not forced to take that path. That path won a quantum election by probability. The photon arrives at the silver surface. Its electromagnetic field drives the sea of free conduction electrons into collective oscillation at the photon's frequency. The electrons re-radiate, re-emit, a new photon traveling backward, away from the surface, in the direction determined by the same constructive interference logic. The new photon has the same frequency and energy as the original. The original photon is gone, its energy converted into electron motion and immediately re-emitted. This process takes place in a silver layer about 100 nanometers thick, and it takes about 300 attoseconds, 3/10 of a trillionth of a second. Meanwhile, the silver surface, every surface, is experiencing Casimir pressure from the quantum vacuum, a tiny attractive force generated by the asymmetry between unrestricted vacuum fluctuations outside the surface and restricted ones inside the metal structure. The force is too small to move your bathroom mirror. But in nanoscale devices, it is an engineering challenge. The reflected photon carries momentum. How much? If asked in the wave sense, the Minkowski question, the momentum is the vacuum value times the refractive index of the silver at that wavelength. If asked in the kinetic sense, the Abraham question, the momentum is the vacuum value divided by the refractive index. Both answers are correct. Both answers describe real aspects of the same photon. The photon carries both momenta simultaneously in different contexts because it is simultaneously a wave and a particle, and those two aspects require different momentum descriptions. 100 years of argument. 2 Nobel laureates on different sides. The answer is yes. And across all of this, across all the quantum complexity happening in 100 nanometers of silver in 300 attoseconds, the final outcome is your face looking back at you, reconstructed from the sum of infinite quantum histories, filtered through constructive interference, shaped by collective free electron behavior, pressured by the quantum vacuum, carrying a disputed momentum, reflecting the documented absurdity of the universe at its most fundamental level. Your bathroom mirror is not a simple reflective surface. It is a quantum machine, executing one of the most sophisticated physical processes in nature, approximately 10 to the power of 20 times per second. You just do not notice because you are used to it. The lightest mirror ever built was made from 200 atoms by physicists in Garching, Germany in 2019. It reflected 60% of the light that hit it through quantum coherence. In principle, 200 atoms at absolute zero can reflect 100%. A perfect mirror made of almost nothing, built entirely from quantum rules. The next generation of mirror technology, the switchable 1-atom-thick tungsten disulfide device from Amsterdam in 2026, can be turned on and off with a voltage in microseconds, with no moving parts, because the reflection itself is a quantum state that can be electrically controlled. Your morning mirror is the old version of this technology. Silver atoms, free electrons, Feynman paths, vacuum fluctuations, entangled photons, competing momenta. Classical in appearance, quantum to the core. The debate between Abraham and Minkowski has lasted more than 100 years and ended in a draw where both are right. The Casimir force was predicted in 1948 and first measured in 1997, 49 years later. Feynman's QED was built in the late 1940s and is still the most precisely tested theory in physics today, in 2026. Every single piece of physics described in this video has been experimentally confirmed, peer-reviewed, and published in scientific journals, accessible to anyone. That is the quantum truth behind the mirror you look at every morning. One last number to close on. Richard Feynman called QED the jewel of physics. The electron's anomalous magnetic moment, a quantity physicists call G-2, is predicted by QED to a precision of 1 part in 10 billion. That prediction has been confirmed experimentally to that same precision across repeated laboratory measurements. No other theory in science has been tested with that level of accuracy, against that level of experimental rigor. And it is that same theory, QED, with its spinning probability arrows and sum over paths and virtual photon exchanges, that tells you why your bathroom mirror works. The most precise theory ever built tells you the truth about the most ordinary object in your home. That is not a coincidence. That is physics. Sources: Feynman, Richard P. QED, The Strange Theory of Light and Matter, Princeton University Press, 1985. Correa, R.A.C., and Saldana, Pablo L. Photon Reflection by a Quantum Mirror, a Wave Function Approach. Physical Review A, Volume 93, February 2016, page 023803. Lamoureux, S.K. Demonstration of the Casimir force in the 0.626 micron range. Physical Review Letters, Volume 78, 1997. Barnett, S.M., and Loudon, R. The Enigma of Optical Momentum in a Medium. Philosophical Transactions of the Royal Society A. Published online February 2010. Max Planck Institute of Quantum Optics, Garching. Quantum Mirror Research, led by Yoon Rui. Published 2020. University of Amsterdam, Hoekstra and Van de Groep. Quantum Phenomenon enables a nanoscale mirror that can be switched on and off. Published January 2026. Pashata, Rudiger. How do mirrors reflect photons? Scientific American, February 20, 2024. Casimir, HBG. On the attraction between two perfectly conducting plates. Proceedings of the Koninklijke Nederlandse Academie van Wetenschappen, Volume 51, 1948.